Welcome to all in the lecture series of functional analysis. Now today in this lecture we see Hahn-Banach theorem. So to see that theorem, first of all we see the definition and after that we start the Hahn-Banach theorem. So first of all we see the definition of sublinear functional. Sublinear functional is a real valued functional P on a vector space capital X which is subadditive. That means here P of x plus y, it is less than or equals to P of x plus P of y for all x comma y belongs to capital X, and positive homogeneous. That means P of alpha x, it is equals to alpha px for all alpha greater than or equals to 0 in R and x belongs to capital X. That means a sublinear functional is a real valued functional on a vector space which is subadditive and positive homogeneous. Then we say that this is a sublinear functional. Now after defining the sublinear functional, we see the Hahn-Banach theorem, extension of linear functional. So the statement of the theorem is, let capital X be a real valued vector space. Let capital X be a real vector space and small p a sublinear functional on capital X. Furthermore, let small f be a linear functional which is defined on a subspace capital Z of x and satisfies f of x less than or equals to p of x for all x belongs to Z. Then the small f has a linear extension f tilde from Z to capital X, satisfying f tilde of x, it is less than or equals to p of x for all x belongs to capital X. That is, f tilde is a linear extension on capital X satisfying 2 on capital X, and f tilde of x equals to f of x for every x belongs to Z. This is the statement of the Hahn-Banach theorem. In this theorem, the given condition is that capital X is a real vector space, small p be a sublinear functional on x, and also we have to given that f be a linear functional which is defined on a subspace Z of x. That means f is a linear functional which is defined on the subspace Z of x. Also it satisfies the condition that f of x, it is lesser than or equals to p of x for all x belongs to Z. This is the given condition. Then as this f which is defined on a subspace Z of x, satisfying this condition, Hahn-Banach theorem says that this f has a linear extension. That linear extension is denoted by f tilde, and this extension, it is from the subspace Z to capital X. That means f tilde is a mapping which is defined on capital X, which also satisfy the same condition that f tilde of x, it is lesser than or equals to p of x. Now, but for all x belongs to capital X, because here f tilde is defined on the whole space capital X. That is f tilde is a linear functional on capital X satisfying this condition, and f tilde of x equals to f of x for every x belongs to Z. That means for every value of the subspace, its image under f and f tilde are equal. Then this is the statement of Hahn-Banach theorem. Now here we have to prove this. Theorem. Now we prove this theorem stepwise, and we prove it in 3 steps. So the first step of this, is the set capital E of all linear extensions G of f satisfying the condition G of x less than or equals to P of x on their domain script D of G can be partially ordered, and Zone's lemma yields a maximal element f tilde on capital E. That is the first step. That means in the first step, we take the set E of all linear extension of f satisfying this condition. Then on this set E, we define a partial order relation. With the help of this partial order relation, capital E becomes a partially ordered set, and on this partially ordered set, we apply the Zone's lemma, and by using that Zone's lemma, we are getting the maximal element of E, that is f tilde. After getting this f tilde, in the next step we show that f tilde is defined on the entire space capital X. That means we show that the domain of f tilde it is equals to X, which we show in the second step. And in the last step we show that an auxiliary relation which was used in B. In B we use some auxiliary relation, and that auxiliary relation we prove that auxiliary relation in the part C. In this way we prove Hahn-Banach theorem in 3 parts. So we start with the proof of the first A. So here let capital E be the set of all linear extension G of f which satisfy the condition g of x less than or equals to p of x for all x belongs to script d of g. That means here capital E be the set of all linear extension. That means we write down capital E be the set of all g such that g is a linear extension. It is a linear extension of f and it satisfies the condition that g of x less than or equals to p of x for all x belongs to the domain of G. This is the set E. Now we show that this set E is partially ordered, and we have to show that this set E has the maximal element. So first of all, as we define E like this, then clearly capital E not equals to phi, since as here we have to given f as a linear functional satisfying the condition that f of x less than or equals to p of x, and therefore E not equals to phi since f belongs to E, because as f is a linear extension of itself, as domain of f we can write it as domain of f, it is contained in domain of f, and for all x belongs to the domain of f, we know that f of x it is always equals to f of x. This is trivial case, but here from these two conditions we say that f is a linear extension of itself. That is small f is a linear extension of itself, satisfying f of x lesser than or equals to p of x for all x belongs to the, actually these are all the given condition, but we just use it to show that f is the member of capital E, and therefore f belongs to capital E, and hence E is non-empty. Now on this set E we define a partial ordering. On capital E we can define a partial ordering. A partial ordering by G lesser than or equals to H if and only if small h is an extension of G. In this way we define the partial ordering on capital V. As E here we show that this is a partial ordering, but we prove that it is, this relation is a partial order relation. The above relation, the above relation is partial ordering, since for each G belongs to E, G is an extension of itself. As we show that F is an extension of itself, in the same way G is extension of itself, and hence we can write down G lesser than or equals to G, and therefore the relation is reflexive. This relation is reflexive. Now we show that this relation is antisymmetry. Now we show that the relation is antisymmetric. That is, if G lesser than or equals to H and H lesser than or equals to G, then H equals to G. That is, we have to show. Now to prove here we are considering G less than or equals to H and H is less than or equals to G. As G lesser than or equals to H implies that small h is an extension of G. Small h is an extension of G. That means the domain of G, it is contained in the domain of H, and G of x equals to H of x for all x belongs to the domain of G. This is the definition of extension, and as H is an extension of G, we are getting this inequality that domain of G, it is contained in domain of H and G equals to H on the domain of G. We give it the equation number 1. Also here another condition is that H less than or equals to G. Also H less than or equals to G implies that G is an extension of H. G is an extension of H. That is, the domain of H, it is contained in domain of G, and G of x equals to H of x for all x belongs to the domain of H. Now from equation 1 and 2, here we observe that domain of G is a subset of domain of H. At the same time, domain of H, it is a subset of domain of G. From this here we are getting that these two domains are equal. Therefore, from 1 and 2 we get domain of G equals to domain of H. Also here we have, as their domains are equal, therefore on the same domain both the images are equal. Also G of x equals to H of x for all x belongs to the domain of G, and that is equals to the domain of H, and this implies that G equals to H. That is G less than or equals to H and H less than or equals to G implies that G equals to H. In the same way we show that this implies that the relation lesser than or equals to is antisymmetric. This relation is antisymmetric. Now after showing that the relation is antisymmetric, now we have to show that this relation is transitive. Now we show that the relation less than or equals to is transitive. We considering let G1, G2, G3 belongs to the belongs to E, that means all are the extension of F belongs to E such that G1 less than or equals to G2 and G2 less than or equals to G3. Then we have to show that G1 less than or equals to G3. That is we have to show. Now to prove it here, as G1 less than or equals to G2 implies that G2 is an extension of G1. It is an extension of G1, and G2 less than or equals to G3 implies that G3 is an extension of G2. G2 is an extension of G1 implies that domain of G1, it is a subset of domain of G2, and G1 of X, it is equals to G2 of X for all X belongs to the domain of G1. That is the meaning of G2 is an extension of G1. In the same way, G3 is an extension of G2. This implies that domain of G2, it is contained in domain of G3, and G2 of X, it is equals to G3 of X for all X belongs to the domain of G2. Now combining these two equations, if I am giving it the equation number 3 and 4, therefore combining the equation 3 and 4, we get combining equation 3 and 4, we get domain of G1 which is contained in domain of G2 and it is contained in domain of G3, implies that domain of G1, it is contained in domain of G3. Also here we have G1 of X equals to G2 of X for all X belongs to domain of G1, and G2 of X equals to G3 of X for all X belongs to domain of G2. Also for all X belongs to the domain of G1, but it is contained in domain of G2. Domain of G2 is contained in domain of G3. Therefore, for all X belongs to the domain of G1 implies that X belongs to the domain of G2, and it implies that X belongs to the domain of G3. That means if X belongs to the domain of G1 implies that it is contained in domain of G2, at the same time it is contained in domain of G3. Then in this case we have, as it is contained in domain of G1, but this implies that G1 of X equals to G2 of X, and therefore this implies that G1 of X, it is equals to G2 of X. Since X belongs to the domain of G1. Also, and G2 of X, it is equals to G3 of X, since X belongs to the domain of G2, as we get here. And therefore here we get that therefore G1 of X, it is equals to G3 of X, because G1 of X equals to this and this is equals to G3 of X. Therefore we are getting that G1 of X equals to G3 of X for all X belongs to the domain of G1. That means we are getting that is domain of G1, it is a subset of domain of G3, and G1 of X, it is equals to G3 of X for all X belongs to the domain of G1, and this implies that G3 is an extension, it is an extension of G1, and this implies that the relation lesser than or equals to is transitive. In this way we are showing that this relation is reflexive, antisymmetry and transitive, and therefore the relation and therefore the relation less than or equals to is a partial order relation, is a partial order relation defined on capital E, because it is defined on the set E, which is the set of all linear extension of f satisfying the condition that g of x less than or equals to p of x, and therefore capital E becomes a partial order relation. On this partial order relation, we have to apply the zones lemma, and the statement of the zones lemma is that, this is the statement of the zones lemma. The statement is that let capital M not equals to 5 be a partial order set. Here we show that our set capital E is a partial order set. Suppose that every chain C subset of M has an upper bound, then capital M has at least one maximal element. Capital M has the condition that every chain in M has the upper bound, then capital M has at least one maximal element. Here we have to find out the maximal element of capital E. That is we have to prove in the first part. We have to show that capital E has the maximal element. So to get that maximal element, we use here zones lemma, and according to that zones lemma, we require capital E is a partial order set, and we prove that here capital E is a partial order set. Now after that, here we have to show that now every chain in capital E has an upper bound. If every chain has upper bound in E, then we get that capital E has at least one maximal element. So in next step, we have to show that we consider the chain in capital E, and we have to show that this chain has the upper bound. So we start with let C subset of E be any chain in capital E. Now it is any chain in capital E. It means that any two elements in C, they must be related to each other by using this relation. Be any chain in capital E, and now we show that the chain C, which is contained in E, has an upper bound. So to find out this upper bound of this C, here we define G cap. We define G cap as G cap of x, it is equals to G of x if x belongs to the domain of G, and here this G belongs to C. G is a member of the chain C, and here we define G cap of x, it is equals to G of x if x belongs to the domain of G, where G is the element of C. In this way we define the G cap. Then G cap is a linear functional. Then this G cap is a linear functional. It is a linear functional because G cap of x, it is equals to G of x, and this G is a linear functional. Therefore G cap is also a linear functional, and therefore we write down that G cap is a linear functional. Also the domain of G cap, the domain being domain of G cap, that is equals to the union of all G belongs to C domain of G. That means we are considering all the elements of C and taking the union of all their domains, and the union of all this domain, it is equals to the domain of G cap, because we define here G cap like this: G cap of x, it is equals to G of x if x belongs to the domain of G, and therefore the domain of G cap, it is nothing but the union of all the domain of G where G is the member of C, which is a vector space. Since C is a chain, which is a vector space since capital C is a chain. Now it is a vector space because here these are all the vector spaces. Domain of G, where G is the element of C, that means G is a linear functional and therefore its domain is a vector space, and as its domain is a vector space, domain of G cap, it is nothing but the union of all this domain. Each domain is a vector space, therefore this union is also a vector space because here C is a chain, and as C is a chain, that means any two elements of C, they must be related to each other, and therefore we are getting that domain of G cap is a vector space. Now domain of G cap is a vector space, and after defining this G cap, now here we show that the definition of G cap is unambiguous, because here if we are considering, as here we are defining the G cap of x, it is equals to G of x if x belongs to the domain of G. But if we have this x which belongs to the two domain, then what is the value of G cap of x? We see it, that we write down the definition of G cap is unambiguous. Is unambiguous since if x belongs to the domain of G1 intersection domain of G2. That means here x belongs to the domain of G1, but when x belongs to the domain of G1, we need G cap of x, it is equals to G1 of x. But in the same way, x belongs to the domain of G2. At this time, when x belongs to the domain of G2, at that time we need G cap of x, that is equals to G2 of x. And therefore, here we have with G1 comma G2 both are the elements of C. And as G1 and G2 both are the elements of C, we have G1 less than or equals to G2 or G2 less than or equals to G1. But if we consider, suppose without loss of generality, we suppose G1 lesser than or equals to G2. When G1 lesser than or equals to G2 implies that G2 is a linear extension of G1. And when G2 is a linear extension of G1, this implies that domain of G1, it is contained in domain of G2, and G1 of x, it is equals to G2 of x for all x belongs to the domain of G1. And then in this case we have G1 of x, it is equals to G2 of x for all x belongs to the domain of G1. And as x belongs to the domain of G1, this implies that G cap of x, it is equals to G1 of x. Similarly, x belongs to the domain of G2. This implies that G cap of x, that is equals to G2 of x. As here, when x belongs to the domain of G2 implies that G cap of x, it is equals to G2 of x. But here we know that G1 of x, it is equals to G2 of x, because here x belongs to the domain of G1 as well as domain of G2, and therefore here as x belongs to the domain of G1 as well as the domain of G2, and this implies that in that case here we are getting that this implies that G cap of x, that is equals to G1 of x as well as here G2 of x, because here we know that G1 of x equals to G of x for all as x belongs to domain of G1, and here x belongs to the domain of G1. Therefore, we have this equality, and in this way we show that the definition of G cap is unambiguous because it is independent of the particular choice of representative. That means here g cap of x, it is also equals to g1 of x, as well as it is also equals to g2 of x, because it is independent of the particular choice of the representative. And therefore here we are getting that g cap is unambiguous. It defined unambiguously. Now after this, also for all g belongs to C, we have g lesser than or equals to g cap, since domain of g cap, that is equals to the union of all the domain of g such that g belongs to C, it always contains the domain of g for all g belongs to the C. And therefore here, that is domain of g, it is always contained in domain of g cap for all g belongs to C. Also by the definition of g cap, we know also for all x belongs to the domain of g, we have g cap of x, it is equals to g of x. It is by definition of g cap, and this implies that g lesser than or equals to g cap for all g belongs to C. And this implies that as g cap, it is always greater than or equals to g for all g belongs to C. This implies that g cap is an upper bound. It is an upper bound for C. And as it is the upper bound of C, but C be any arbitrary chain in capital E, but C subset of E was arbitrary. This chain is arbitrary and this chain has the upper bound. That means every chain in E has an upper bound. Thus, every chain in capital E has an upper bound. And as every chain in E has an upper bound, therefore, by Zone's lemma, has a maximal element, say f tilde, such that f tilde is a linear extension of f, satisfying f tilde of x, it is lesser than or equals to p of x for all x belongs to the domain of f tilde. In this way, we are getting the maximal element for the set E. Now, in the next step, we have to show that f tilde is defined on the entire space capital X. That is, we have to show, we prove it in the second part.